Alright, back to this problem. We recall the formula C4H8O2. We have a carbonyl peak. The 1730 wave number information told us that. And then our first peak right here told us OCH2 bonded to something. Note, 4 ppm as the chemical shift means the hydrogens are carbon bonded to oxygen. Integrates to 2, most likely way to get that is a CH2. And we're not sure what it's bonded to on the other side. Whatever it is cannot have hydrogens on it because that is a singlet. And that's about all the information we can get from this peak. So let's go to the next peak. All right, we have this one here at about 3.3 or so ppm. So, well, that's a little downfield. It integrates to 3. Now, what's the most obvious way to have something integrate to 3? Most obvious way is a methyl group. So I'm just going to write CH3 there because that's the most obvious way to have something integrate to 3. Let's see, it is downfield. What could be next to? Well, 3 to 4, 3.3, 3.4 or so. Could be an oxygen. I feel happier when peaks are down at 4, being oxygen. Down at 3.5, though, that's about an oxygen, is about the only thing that will work. But at this point, all we know is whatever it is bonded to does not have any hydrogens attached because it is a singlet. Let's look at our last peak now. It integrates to 3. Again, the most obvious way for that is a CH3. Now, it is down at 2 ppm, about 2.1 ppm. And when we look at the information we already have in our molecule, we know what will bring a proton peak down about 2.1 ppm. Well, that's a carbonyl. A carbonyl will do that. All right. Well, let's see what we have here. Okay, of the pieces, I've got these 3 pieces so far. Carbons, 1, 2, 3, 4 carbons, check. 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, check. 2 oxygens, 1, 2, check. So that tells me these 3 pieces here are my molecule. Now, how do I put this molecule together that A, makes chemical sense, and B, works with this spectrum? Now, some people might be tempted to take this CH3 and hook it up to this CH2, but that cannot work because if this CH3 was bonded to this CH2, then this would be a triplet because these 3 would see these 2. And it's not a triplet, it's a singlet. We could have the CH3 bonded to the carbonyl, but then that would be the whole molecule. CH3, C double bond O, CH3. That molecule would be acetone, but then we wouldn't have this part in the molecule. So the only way this is going to work is to bond this CH3 with this oxygen over here, which means this CH2 has to be bonded to the carbonyl carbon. That gives us the final product here, our final molecule, CH3, C double bond O, O, CH2, CH3. All right, now does that work? Note, this carbon is bonded to a carbon without any hydrogens on it, so no splitting here. These 3 will be a singlet. Whoops. Whoa, I messed up. This doesn't work, does it? I drew this incorrectly. Pencil. This carbonyl is bonded to the CH2. And that CH2 is bonded to the OCH3. As you can see, it's always a good idea to check your work. You think you're doing it right, but then you write down the wrong answer, actually wrong from your thinking. So let's check it again. Does this molecule work with our spectrum here? Well, CH3 next to a carbonyl. No splitting of these 3 protons because there's no protons on the carbonyl, so that's singlet at 2, integrates to 3. Note, this CH2 is next to a carbonyl and next to an oxygen. Note, carbonyls move things downfield between 3 and 4. Or excuse me, oxygens. Oxygens move things downfield between 3 and 4. Carbonyls tend to move things down a little bit. So that makes sense that this peak here, this CH2, is at 4 ppm because you've got the oxygen pulling it downfield and the carbonyl is pulling it downfield a little bit also. And then this CH3 is on the other side of that oxygen. It is not quite as far downfield as the CH2 is because it's only the oxygen pulling it downfield, not both the oxygen and the carbonyl. Either way, the CH3 is bonded to an oxygen, not a carbon. Therefore, it's a singlet, no splitting, and we get that singlet there. All right. Let's go through one more. Got some glare here. All right. So what do we see here? First, if you're looking at the description in your book, page 565, it notes that it has the molecular formula C8H11N. All right. So, let's examine what we have here. The first thing to notice, again, remember I always like to start on my left and move to the right because left is where the fun stuff's at. Here I have a couple of peaks, a little downfield of 7 ppm that integrate to 5. Now at this point you might be thinking this looks a little complicated. This is like the easiest thing ever because chemical shift a little above 7 means it's an aromatic ring, a benzene ring. Integrates to 5 means there are 5 hydrogens on this benzene ring. Note, a benzene ring has 6 carbons, so if there's 5 hydrogens on it, that just leaves one spot open. We have a monosubstituted benzene ring. That's pretty nice. You see something around 7 ppm, a little downfield of 7 ppm, integrates to 5. We don't have to worry about what the peaks look like. We don't have to worry about spin, splitting. It's a monosubstituted benzene ring. All right. So, well, that took care of 6 of our 8 carbons. We look at our next peaks here and we see, all right, they were so close together that they had to be expanded here, but we see that it integrates to 2. Now what's the most likely way something integrates to 2? A CH2. It's a triplet. It's a triplet, which means it has 2 hydrogens next door. What's the most obvious way to get 2 hydrogens next door? Another CH2. Okay. Chemical shift, it's down at 3 ppm. Now what's going to bring something down to 3 ppm? Well, benzene rings can bring something from 2 to 3 ppm, but also nitrogens. We know there's a nitrogen in here. A nitrogen can bring it down to 3 ppm. So at this point, I am betting you there's the nitrogen on there. Let's look at this other CH2. It has to be this one. Integrates to 2. It's a triplet, which means there's 2 next door. Well, there's the 2 next door from this CH2 here. And what's going to bring it down to between 2 and 3 ppm? I bet this is bonded to the benzene ring. Well, then what's this? What are these two hydrogens right here? First thing we note, it's a singlet. It's down around 1 ppm here, but that's where we'd expect a CH3 to be, but it can't be a CH3. We know it can't be a CH3 because here are 6 carbons, 7, 8. There's all 8 of our carbons in the molecule. Between the benzene ring and those CH2s, that's 8 carbons. There are no more carbons in this molecule. So whatever those 2 protons are attached to, it's not carbon. What are they attached to? Well, shouldn't nitrogen have 3 bonds? Here it only has 1 bond. I'm betting that those 2 protons are attached to that nitrogen. Let's recall about the chemical shift of hydrogens on heteroatoms. Hydrogens on oxygen or nitrogen can come anywhere. So yeah, down around 1, sure they can come there. We also noted that the peaks tend to be broad, and at first thing you might say, well, that peak doesn't look too broad to me. But we realize this is one single peak. Look at how wide it is. It's not that wide, but can you see the width of this peak is about the same as the width of this one? From here to here, it's about the same as here to here. This is about the same as that one. Realize this one peak has the same width as these 3 peaks. Here are 3 peaks, and all 3 peaks together have the same width as this one peak. So that peak is a little bit broader than your other peaks in the spectrum. And looking at this, then all we have to do, well, is attach this CH2 over here. CH2, CH2, and H2. All right. This is page 565 of your textbook. Start working on the other spectra that you see here. You've got this one here, compound I. This one is what? A here and B here, problem 14.61. I will post answers to these problems in a few days.